Alright, so before we talked about valence bond theory, we had regions of atomic orbitals overlapping, so like you have two s orbitals overlap, or it's possible to have p orbitals overlap like this, or like this, so you get sigma or pi bonds. S orbitals are always sigma bonds because the electrons are always shared between the nuclei, and it works as a good first understanding for what a bond might be, right? So if we're sharing electrons, where are those electrons going to be? Well, it must be something like where they would be in an atom. That's not an unreasonable expectation. The problem arises with the fact that it does not explain geometry at all. So interhybrid atomic orbitals. So what we do is we take those atomic orbitals and we sort of mix them together. We kind of shuffle them into a different set of orbitals by mixing s's and p's and all that, and then even d orbitals. And we sorry, I gotta shuffle my papers here. And so we can get something that will actually account for the geometry of the molecule, which is where valence bond theory falls flat on its face. Because everything should be either 180 or some 90, something like that, because that's what atomic orbitals are, 180 or 90 degrees from each other. So our molecular geometries are clearly not only those values. We can have 109.5, we can have 120 degrees. So how does that happen? Well, that's what we're going to talk about here. So this is great for explaining geometry. The problem is we kind of just take the geometry and then we fold it into this. This doesn't really give us the geometry as much as the geometry gives us this idea. So it's a little bit backwards version of explanation. And as a result of that, it is useless for basically everything else. So it's great for geometry. And it doesn't work great for those lone pairs squeezing bond angles either. So only for ideal geometries. So, bond energies, no explanation for that here. Bond lengths, nah, that's not going to happen. Magnetism, no, not going to happen. Just list goes on and on. So it works with geometry, doesn't work for anything else. So here's kind of the basic idea. Okay. We take our atomic orbitals, and I think I said this already, but let's get it in writing. So we take our S, our P, our D's, and there's more than one P orbital. So S orbital or P's or D's, they're all from the same n value. So maybe it's the 2s and the 2p orbitals get mixed, or the 3s and the 3p, or the 3s, 3p, and some of the 3d orbitals get mixed. So we're going to take those orbitals, and they are going to be, I like the term remixed. So basically you just kind of edit like Pitbull in there or something, I don't know. Or the term that, the correct term, the official term would be hybridized. So they're just kind of mixed together, and we're going to get different shapes. Because we're going to get different shapes because we are mixing them into new orbitals. And these new orbitals are actually going to be better for bonding. So, I'm going to go in a little bit different order than the book in my explanation. Your book goes one direction, I'm going to kind of go the other. So as an example, let's look at carbon. Just carbon. So we're just going to look at how the atoms' atomic orbitals get rearranged, and then we'll talk about the simplest molecule we can make with it, which will be CH4. Alright, so carbon, its valence electrons, we're not going to worry about the inner, has a full 2s orbital, and then in the 2p orbital there's 2 more electrons. So there's 4 valence electrons, and these are organized, by the way, by energy. 2s orbitals down here because it's less energy than electrons in the 2p orbitals. These are higher energy orbitals. And our p orbitals kind of look like peanuts. Our s orbital is just a sphere. And so what we do, we're going to mix these all together. And what we get is something that's in the middle in terms of energy. And we call these sp3 hybridized orbitals. So these are atomic over here, atomic orbitals. These are hybridized. So they are mixed. So what I've done is I have taken an s orbital, and I've taken 1, 2, 3 p orbitals, and I've mixed them all together to get 4 new orbitals. So I've taken an s, and I've taken 3 p orbitals. So sp3 gives me 4 new hybridized orbitals. And now they're all the same energy level, and I have 1, 2, 3, 4 valence electrons to put in here. So they go in here like this. Alright? And this should make a little more sense if you look at just the electron arrangement. We don't really look at what we did. Because remember, I think it's a pretty good instinct now. Carbon's going to make 4 bonds. How does this help us make 4 bonds? These aren't unpaired electrons. Remember, valence theory says, or valence bond theory says, half-filled orbitals overlap to create a bond. Well, there's only 2 half-filled orbitals. So according to that, carbon should make 2 bonds. But that's not the case. It makes 4. So what happens? Well, now we have 4 half-filled orbitals. It's going to make 4 bonds. And what does this look like? So we had, a peanut that looked like this, and this, and this, and a sphere. Right? Now what we have is we have our nucleus, and then there's kind of a lobe that goes up. There's a lobe that goes kind of to the side here, and let's say this is, I don't know, how about 109.5 degrees? All right. So there must be another orbital. So this is what they all look like put together. And there's one kind of going forward and one going back. And so what it is it's a tetrahedral arrangement. That's what it looks like. Or a really, I don't know, what is that, bird foot? I don't know. My mom is an artist and her son is a chemist. And I'll leave it at that. So, I will throw the figures from the book up in the supplementary materials so you can easily reference those along with the lectures. That will show much better, rendering of what these look like. But essentially it's, it's your tetrahedral. You got one that goes up, you got one that kind of goes 109.5 and then 109.5 and then 109.5. So there's 4 groups. And so each of these is an orbital. And so that gets us an area where we can overlap here and make a bond, an area where we can overlap here and make a bond, over here make a bond, and here make a bond. So we can make 1, 2, 3, 4 bonds, which we're dealing with carbon, right? It only needs, it needs, I don't know about only, but it needs 1, 2, 3, 4 electrons to fill its valence shell. So it's going to make 4 bonds, right? Everything we talked about before is correct. We're just adding details to it. So where are those electrons going to be when it makes those 4 bonds? Well, according to hybrid atomic orbitals, this situation right here. So if we look at CH4, I'm going to move it over here so I have a little bit of room in the middle. I've got my carbon. And it's going to have 4 sp3 orbitals. So these are all sp3 orbitals coming off the carbon. What about hydrogen? What does hydrogen do? Well, it has the 1s orbital. Are there any other orbitals we can mix with that? Are there 1p orbitals, 1d orbitals? No, there's only the 1s orbital. So hydrogen cannot have a hybridized atomic orbital, and so it's just going to be spheres. Just 1s. So it is actually going to have atomic orbitals. And so that's what makes this so simple to draw for me, is I just have to draw circles, and I still have moderate success at that. Alright, so we still have these areas of overlap. That gets us chemical bonding. So that idea isn't wrong. It's just being built on. And if we look at our bond angle, as you can clearly see from my beautiful drawing, 109.5 degrees. Go ahead, get a protractor out, measure that. That is totally not like a 90-degree angle or something. That is 109.5. And so again, this would be organized in 3D space. And so what we have is that situation where carbon is doing that number, right? It's got flat, flat, kind of coming out towards you and going back. So that's what we're talking about there. All right, so all of these are single bonds, by the way. That's what carbon's doing. It's all single bonds. What about double bonds? What do those look like? How do I get a double bond? Well, definitely be tricky trying to get a double bond out of something like this, but this was a molecule that didn't have any. So what do? We mix our orbitals together in a different way. And so, for example, if we look at formaldehyde, we'll have to have a different hybridization. We have a different geometry, right? This is going to end up being trigonal planar because it has 3 groups. They're going to be flat, but 120 degrees. Okay, that's what's happening with the carbon. So, how does that happen? We have a double bond, we have different geometry. The carbon is going to be sp2 hybridization. So we're going to mix an s orbital and then only 2 of the p orbitals. And so it's going to look like this. I'm sorry, 2s, 2p. Now before we mixed all these together, now what we're going to do is we're still going to have one 2p orbital with 1 electron in it. And we're going to take the s orbital and the other 2 orbitals from the 2p set, and we're going to mix them together to get a set of 3 orbitals that are sp2, all with 1 electron. So I still have 4 half-filled orbitals. But now one of them is an unhybridized atomic p orbital, and the other one is hybridized sp2 orbitals. So 2 sets. So this is an unchanged 2p orbital. So it looks like that. The sp2 look like this. They're going to be 120 degrees. This thing's flat as a pancake, and then it's just 120, 120. Those are all my orbital groups. And then going straight up and down from that, my p orbital. So it is perpendicular to all of this. And that's going to be very important here in a second. So these are the sp2s. And then straight up and down is going to be the p orbital. Alright? And so if we look at what carbon is doing, and oxygen is going to be doing the exact same thing. So oxygen has 3 electron groups around it as well. It has a bonding group, and then it has 2 lone pairs. So instead of having bonds with hydrogen, it's just going to have 2 electrons already in those. And so if I draw the carbon, and then I draw the oxygen, oxygen is just going to have lone pairs in it. Carbon's going to bond to hydrogen. Okay, so these are my overlap regions. These are full, so they don't need to be used for a bond. And so we have this situation where all this is happening. And then I also have these p orbitals. Going above and below. So we have sp2, and then we have 2p. And again, the book's going to have better pictures for this. But here's what happens. These overlap into each other. Okay? And so what we get is we have a sigma bond here, and then we have a pi bond that's half above and half below. And so we have the carbon and the oxygen with a single bond, and then above that is half of a pi bond, and below that is half of a pi bond. So they're not being shared in the middle, they're being shared above and below the atoms. And so a double bond and if you think about it, hopefully this makes sense because we're already sharing electrons in the middle. We can't squeeze more electrons in there, so we start fitting them in between the atoms, but not directly in between, but above and below. So we have one sigma and one pi bond. Okay. And the pi bond is from p orbitals, and the sigma bond is from sp2 orbitals. So hybridized orbitals for the sigma bond, unhybridized atomic orbitals, because those p orbitals are quite large. And so they actually, when I draw them like this, I'm not drawing right. They will have areas that overlap above and below. They take up a lot of space. But it is, you know, half down here and half up here. I think that's the trickiest thing for students to recognize. And I will post pictures of this as well from your textbook to help illustrate better. All right, and so we talked about single, we talked about double. What about triple bonds, right? Carry through. Well, let's just take a second to think about this. We had single bonds. I had my two atoms. They went right in the middle. I added a double bond. The middle's already taken. What do? I go above and below. So now, if I have a double bond, I have the middle and the above and below taken. What's left? Where else can I put electrons? In front and behind. So just like I'm above and below, I can go 90 degrees to that, be in front and behind. So that's where the triple bond comes in. That's where we squeeze in a second pi bond. We can't get a second sigma bond, but we can get another pi bond. So we get one sigma, two, pick an alphabet, Joe, come on, two pi bonds. All right, and we do this with sp hybridization. So now we're only going to mix one s orbital and one p orbital. All right, and so what we have with sp, we have our s, we have our p, maybe it's 2s, 2p, 3s, 3p, who knows. And we have two of the p's left, and then we have sp. So we have four orbitals. We still have four orbitals. Two of them are unhybridized. Two of them are hybridized. And these are going to be 180 from each other. And these are going to be 90 degrees. And so what I have is I have p orbitals like this, and then I have the sp orbitals like this. Okay, so they are all perpendicular to each other. And so one sp orbital goes forward, one sp orbital goes backward. So you know, one's here, the other's over here, and then my p orbitals are above and below, perpendicular to each other as well. So it's a little bit weird to draw. And so what we get is, I'm not even going to try to draw this. I'm just going to go straight with the images from the book, have you look at those. But what you're going to see is you have a pi bond that's above / below. In the middle you have a sigma bond. And then you have a second pi bond that is in front / behind. And this is all from p orbital overlap. Pi bond equals p orbital overlap. And then the sigma bond is sp being used to overlap with something. Okay? And so, again, what we have. So if we have our sigma bond, all right, we have a pi bond that's half here, half here. So there's a pi bond running right here. There's a second pi bond in front and behind. So this area is taken by a pi bond. This area is taken by a sigma bond. This area back here, pi bond. This area up here, pi bond. So they're not bumping into each other. They're in different regions of space. And that allows us to get 1, 2, 3 bonds. So we get a triple bond. And that's why we don't go to quadruple, because where the heck is left to squeeze more electrons into that? I mean, are you kidding me? Okay, so oops. Grab the wrong sheet, put it in the wrong place. Alright, so we're not quite done yet. And there's quite a bit we're talking about here, and I'm going to sum it up. There's going to be a very easy way to tell, like, oh my god, what geometry am I dealing with? We'll get to that in a second. But before we do, d orbitals. Well, everything I've shown you has 4 orbitals. That can get us 8 electrons. That's everything that follows the octet rule. What if we break the octet rule? What if we have an expanded octet? What happens? Where do those electrons go? Well, we just bring some d orbitals and we bring them into the mix. So they get added in for expanded octets. And so what we get is, we can mix an s with up to 3 p orbitals. Then we're out of p orbitals. What do? Bring in a d orbital. And so that's trigonal bipyramidal geometry. Or, what about octahedral? If we're going to squeeze, instead of 10, 12 electrons around, what do? We bring 2 d orbitals into play. So we just take our s orbital and we start mixing in p orbitals. We get sp, sp2, sp3, and then if that's not enough, sp3d, sp3d2, because those are the next orbitals we can bring in. We're not going to reach an energy level. We're not going to, have the 2s orbital mixing with the 3s orbital. No, the 2s will mix with the 2p. The 3s will mix with the 3p, but it can also mix with the 3d. And so that's why you don't see those expanded octets in the second row, because, if you look at, like, say, oxygen, n equals 2, so it can have s orbitals, it can have p orbitals, it can't have any d orbitals. There's no d orbitals accessible at that quantum number. There is no room at the address. So, you only see these expanded octets third row and beyond. So it's another explanation for something we've already talked about. You guys love that, right? You'd love to learn how to tie your shoes 3 different ways, right? So, how do we know what hybridization? I'm not even going to draw these because it's well beyond the scale of my art abilities. I already said I'm going to post the pictures. Look at the pictures. Pictures worth 1,000 words, or 2,000 of the words I say because I waste a lot of words. So how do you know which hybridization? I've already kind of hinted at it, but let's make sure that this is crystal clear. How do we know? There's actually a really easy way. So I went through all this long explanation of showing you where the electrons were and explaining the organization and everything. And really all you have to do, once you understand that, you can grasp this shortcut, and this is much simpler. So you just look at the number of electron groups, or not groups, areas, it's a better word for it. And so you just look at the total number of bonding areas and lone pairs. If you see 2, sp. 3, because we have two, it means 2 orbitals get used. 3 orbitals get used. So sp2. 3 does equal 3. That wasn't wrong. I'll point that out. But, so if you see, a bond and you see a lone pair and 2 bonds, sp2. Whatever it might be. Double area, like what was it? Let's go into the Wayback Machine here and look at this. This had 1, 2, 3 groups. 1, 2, 3 groups. So it was sp2. This oxygen, by the way, has 1, 2, 3 groups. It is also sp2. That's what I was talking about. So that's how we fit those groups around. That's the hybridization we do. So if there's 4, you might see the pattern already. What do you think it's going to be? Well, I'm going to have 1, 2, 3, 4 orbitals for that. If it's 5, you might go, oh, it's sp4. No, because there's only 3 p orbitals. We have to bring d orbitals into the mix. We've run out of p orbitals to add, so now we're going to add d orbitals. This is like, you're doing a baking recipe and you're like on the edge and you're like, oh, I don't know if I have enough sugar, and you start subbing in some brown sugar as well and just hope it works out. And then you find out that brown sugar is way more delicious anyway, and so you're like, well, then I'm going to try adding even more, and you get sp3d2. And so that's 1, 2, 3, 4, 5, 6 orbitals to be able to put electrons in 6 places. 1, 2 orbitals to put electrons in 2. 1, 2, 3 orbitals for 3 places. 4 orbitals, 1, 2, 3, 4 for 4 locations. 1, 2, 3, 4, 5 for 5 locations. And it's because, well, the reason we have to bring those d orbitals in again is I go 3s, 3p. I'm out of p orbitals. When I add 3 of those, I start bringing in d orbitals. Can't do that for n equals 2. And remember, hydrogen doesn't hybridize at all because it doesn't even have p orbitals to bring into the mix. So it's just 1s. It's just a 1s orbital under all the theories we've talked about so far. So, if we look at something like PCl5, there we go. 5 phosphorus. You can set this up. You can draw the structure. I think you probably already have. I tend to throw this one around a lot. We've talked about drawing this dot structure, this loose dot structure. We have talked about formal charges to know this is the best structure. We've talked about how phosphorus can have an expanded octet because it's in the 3rd row. So it has 2, 4, 6, 8, 10 electrons around it. But now what we're saying is it has 1, 2, 3, 4, 5 areas with electrons. So it is sp3d, 1, 2, 3, 4, 5 areas of electrons. So it has sp3d hybridized orbitals. We've also talked about the geometry, right? So, this bond angle, 120 degrees. This right here would be 90. This is trigonal bipyramidal. It's a hard word to spell apparently. And so it has a trigonal bipyramidal. I almost made it clean through this video until we're near the half-hour mark. Molecular geometry. It also has a trigonal bipyramidal electronic geometry because it has. So molecular geometry cares whether this is a bond or a lone pair. And I don't know if I did a good job of explaining this last week, but electronic geometry does not. And so both of them are, if they're all bonds, they're both the same. And the molecular geometry will change as lone pairs are added in. The electronic geometry does not. Now, what is the hybridization for chlorine in this situation? What's going on there? Well, it has 1, 2, 3, 4 areas of electron, of electrons, I should say, just areas with electrons. So it has 3 lone pairs and a bond. So it's sp3. That's where we are now, talking about what hybridized orbitals are there. So that's the shortcut. Now, understanding what this line represents in terms of what's overlapping, well, we're going to have an sp3 overlapping with an sp3d orbital from phosphorus. So they're going to be different types of orbitals overlapping. But they are both hybridized orbitals. These lone pairs are just sitting in sp3 orbitals, hybridized orbitals, that just aren't being used for bonding because they're full. Alright, so that will do it for this section. This is always a big idea in this chapter, so hopefully it's clear. Like I said, you're going to want to look at those pictures because there's my drawing ability and then there's the ability for a computer to render a picture. One of them is up here. I'm below the table. You can't even see my hand, but I'm waving it below the table. That's where I am if the computer's here. So go ahead and look those over. Make sure those shapes make sense. Make sure that idea of pi bonding and where those pi bonds are happening and the fact that it is half and half. Remember, that's important. And also, that's why a double bond, an interesting feature. A single bond, you can rotate. It's like an axle. A double bond locks you. The whole thing, you can't rotate two sides independently of each other anymore. They have to rotate together. So instead of being able to do something like this, now you're double bonded, you have to flip it like a pancake. You can't just spin it like two independent wheels. So the reason for that is that pi bonding locks it in. Alright, and so next we're actually going to talk a little bit more in depth about that pi bonding and a very interesting feature that happens and is really important in a lot of like organic compounds, as well as a few other things. So that's what we're going to talk about next. We're going to talk about what's called conjugate pi bonding. So the idea of pi bonding is actually going to get built on a little bit more, and it's just those p orbitals overlapping above and below the sigma bond. They have areas of overlap, therefore the electrons get shared by unhybridized p orbitals. Okay, so maybe start out, just make sure that the idea of the hybridized orbitals makes sense by themselves, and then definitely by the end you want to make sure that you can easily identify, and here's the shortcut, what type of hybridization you're dealing with on any given atom.